is a senior researcher within Design++ at ETH Zurich in the Center of Augmented Computational Design in Architecture, Engineering, and Construction Practices, and she is a co-lead at the Immersive Design Lab. So, thank you.
Thank you. In contrast to the other two speakers, I only recently started to work with machine learning. So actually core interests are computational design and human-machine interaction, or more specifically, human-machine interaction with machines. So today I actually want to make with you some sort of a detour because moving from early investigations, which I did with robots, so studying human-robot interaction, and then making a big jump and then talk about human-computer interaction using extended reality for AI systems and highlight commonalities and correlations. So I will show you some examples that have in common the purpose of investigating the design space or design process and how an ideal partnership model between humans and machines, may those be physical or digital, look like. So this title, Translations Between the Imagined, the Perceived, and the Executed, actually refers to the process of designing, which Schoen refers to as a form of artistry and making, where learning about a specific topic or design emerges through actions, may they be conscious or unconscious, and heuristics. So the designer learns how to design by knowing and reflecting in action, reinterpreting and re-elaborating actions in the particular moment where the act of the design takes place. And this is how the designer develops this tacit knowledge, which is hard to explicitly describe, as stated in this quote here. So with the advent of digital model tools, this cognitive model of design thinking has transgressed to become more and more computational. As architects, we use different tools of digital and physical nature that support these processes. Advanced digital tools are capable of mapping relations and mutual dependencies. On the other hand, we have those physical tools that allow a sensible dialogue with materials and their respective properties. But however, they lack the possibility of representing semantic relations or information other than the ones inscribed in the physical properties, and therefore hardly meet today's need to process all kinds of information along the design process. So, like I said, it's a detour that started actually 10 years ago with my colleague Katrin Dörfler and I. We investigated how to purposely combine the two worlds or the two tools or instruments, digital and physical worlds, by using actually a robot. So we were both caught by a fascination for robots, not merely for automation, but actually as an interactive tool to use in a design process. So envision the robot as a co-worker of designers and builders in constant interaction with the designer. So this was one of the first tests we used to the iPad's orientation to control actually also the orientation of the robots and the factory. So to explore these questions, we developed a system called SANS, a Sensor and Actuator Network System. In the system, people and robots would be connected with various sensors like a camera, iPad, or a 3D digitizer circulating information from the physical world to the digital model to establish a possibility for humans to actively take part in the fabrication process, so by influencing and moderating as this fabrication progresses. Our system allowed us to connect any sensor input with various CNC machines or robots, only with a few modifications. So in this case, a 3-axis milling machine. Here we tried the simultaneous milling of a 3D digitized surface where the algorithm is simply the translation of the coordinates one-to-one from the digitizer to the 3-axis milling machine. The scanning of the surface is a complete manual process, and therefore the result is not only a copy, although it undergoes a digital process, but the imperfections of the hand movements are inscribed on the surface. So one could imagine to take this a little bit more further, more interesting, in applying another digital process on top, so scaling it or smoothing those movements. What you then have is somewhat a process related to teleoperation that is very much common in medical surgeries. So what we effectively tried to combine was the process of digital design with the process of digital fabrication. So the designs don't have to be frozen before the fabrication and design can happen. So the designs don't have to be frozen before fabrication, and that this design can happen in constant interaction with machines during fabrication.
Can I have your attention, please? Can I have your attention, please? We are with the fire alarm test. This is only a test. Where we're conducting a fire alarm test. This is only a test. Disregard all fire alarms.
Only here. It's about to go off. Yeah. Or is it just a speaker? You know, we have.
He said these regard the alarm, so that means these don't have to.
That's right. Yeah.
Oh, good. So design, as you know, is a complex process. It's non-linear, and it undergoes various phases. You gather a lot of information during the design process and about the design problem, and you make various decisions based on experience and collaborative knowledge. So another question that we were targeting is how to find the balance between rational and intuitive decision-making in this process. The following experiment we did in the very first beginning of our research was a robot painting, and we used an iPad as an input device. We choose a growth algorithm, then pre-take growth algorithm, which has the feature to develop over time and can progress during process input during the runtime of the program, influencing this growth pattern. So here the point was to add more complexity to the process. So I'm standing here with the iPad positions that mark the positions of certain seats, which the growth algorithm then takes as input to develop this concrete structure around. But what you can observe that it is kind of difficult to understand the causality between the user inputs and the reaction of the system, not only because of complexity, but also because there is a delay in time of execution. So as a user of a system, what you might lacking is the feeling of interaction and the possibility to really change the outcome. So besides that, the algorithm is very dominant. Different input parameters over the iPad will still lead to similar results. Also, the shown experiment is also a linear process just in one direction. So input influences the output. There is a certain feedback, but just through the designer who makes the next decision according to the current state. The process becomes though more interesting when sensor devices are monitoring the current state, where extracted parameters can be used as input for the algorithms, creating feedback loops between machines. So this feedback can then be used in various ways. Together with a properly designed algorithm, it can help to create robust and fault-tolerant systems capable of recovering from errors or improper user inputs. It enables user interaction without using a dedicated external input device, but through direct manipulation of the physical object. So, sorry, I had problems before with my presentation. That's why Jorge stepped in, and now I feel I have the same problem again. Okay. Okay. So what feedback also allows to more consistently explore and balance the level of autonomy and collaboration between participating agents. There exists a loose definition for autonomy for humans or machines as the extent to which a system can carry out its own processes and operations without external control. There also exists a more specific definition of autonomy that relates to robots to be the extent to which a robot can sense the environment, plan based on that environment, and act upon that environment with the intent of reaching some goal without external control. And there is actually two major groups or opinions on autonomy's implications in the human-robot interaction context. The main opinion suggests that higher autonomy yields to less interaction between humans and robots, in which research aims to maximize system performance, so for example, autonomous driving, with minimal human intervention. But the contrasting and far more interesting perspective actually suggests that there is a positive correlation between autonomy and collaboration only with higher levels of autonomy in robots and machines. A more balancing relationship can be established where humans and robots can work together on a common goal with a proper communication and a completing skill set. So what we tried is actually to embed feedback in the process. With rather limited tech know-how and off-the-shelf systems at hand, we built a custom sensor table that could track elements in 2D. So inside the box, there's a camera mounted monitoring the surface, analyzing the image, and then this information could then be used within a fabrication algorithm. We started here to explore fabrication processes using rule-based algorithms in combination with sensor feedback. Okay, no problem. Well, here you see a robot is laying thread onto a surface according to an internal closed-loop control algorithm. The camera tracking then allows the robot to react to user input at any time. So putting more thread at the positions where the user indicated. So the user could actually intervene and moderate the process. And we actually thought this direct manipulation of the physical object far more interesting than via any sensor or input device. So in extension to this process, we started with tracking small randomly distributed wooden cubes from underneath the surface. So in the digital domain, we inform those cubes with a mass. They represent particles attracting one another, what you can see visualized on the right. So in every iteration, the robot would pick and place one element, and according to the calculations, after evaluating the camera feedback of the current state, without the need of, we don't need to store those objects because they are constantly resourced every time. So when mistakes occur, so sorry, this is the wrong, I'm very sorry. I had to rebuild my whole presentation just 10 minutes ago. So actually what you see here is, you should see here some clustering, but I will then just switch to the next image. Well, later we aimed to take the concept further into 3D, so the piling of sticks in non-predetermined matter. This is a video of a workshop we held at the conference 2012. So a colleague of us is placing some sticks on the table, so carefully defining an initial state. And in the back, you see the projected screen showing the Rhine viewport, and you also see that there is actually no model beforehand, so only rules of how to build up that structure. In Rhino, you also see that search that is performed in order to find a stable place for a newly placed stick. So as soon as one is found, the robot will place the stick on the two others. And well, this search can go endlessly until I stop placing new sticks or until no available position for a newly placed stick can be found. Good. So that was the excursus. A few years have passed since that, and actually many research groups in architecture and digital fabrication have started to look into research of the fields of human-computer interaction, human-robot collaboration, to bring these concepts further to architecture, design, and building. I just wanted to highlight two of them. So, for example, on the left, you see Roma, a system that allows users to design 3D digital models in AR while a robotic 3D printer fabricates the design at the same time in the same space. So like that, the users can integrate physical constraints early in the design process and design and print directly onto the existing object. On the right, FormFab is called this process. And this is an interactive fabrication system that can change a workpiece shape constantly while the user is interacting. They use the process called formative fabrication to reshape the existing material. The user interactively controls a pneumatic air pump that applies either pressure or vacuum to a thermoplastic sheet, thereby pushing the material outwards or pulling it inwards. So what's important in both examples is that designer and robot share the same working environment, both in designing and fabrication. So the other two examples I want to show you understand the robot as extension to the human body. So on the left, you see the third thumb, which is a 3D printed thumb extension for the head, for the hand. The project here investigates the relationship between the body and the prosthetic technologies in new ways. On the, well, images don't seem to work. So, and then the right-hand side, actually, you see the reverse, that actually here the robot is extended by a human to paint on a canvas. I don't know.
Is this like frozen?
No, I think yeah, but I think it's also, I cannot escape neither, so I guess my computer just crashed. No. Okay. Oh. Yeah.
It just shocked me. Oh no. It's
No.
not English keyboard.
You know.
It's perfect. Yeah.
No.
You guys know.
No, I'm sounding useless. Apologies. She's gonna end the class, I think.
Yeah.
You could be scared.
Not a good day today for my computer.
It's just part of the day. It's not. Is it completely frozen?
At the moment, it seems completely frozen, actually.
Is it HTML? You totally close PowerPoint?
I terminated it. Yeah,
It's still on now.
yeah, it's still running.
No?
No, sorry.
It's frustrating.
I think it's restart.
I think you want, and that's okay. Access and performance.
Na, das sind die Videos, die funktionieren nicht. Hm?
Is
Do you
it's
want
like,
to-
is it on a flash drive?
It's funny. So actually, in this time, well, she's probably.
Yeah. I mean, it is rebooting.
Is it?
Yeah, it's just taking its sweet time to show up there. No, but it's like the computer's off,
Ah.
and it's still showing this. Could it be? Oh, there we are.
There's a sort of. Yeah. An internal thing. Yeah. Very nice. Just right. I think yeah, it's fun. It's not done for I don't know. They're hot. They get us really hot. You really want to be cold. Now it's
So this is a good training.
Okay, I'm very sorry. I hope now.
I'm great.
Yeah, some of the scenes. Earlier, because I can shop.
I hope there is no more interruptions anymore. Yeah. I will continue here. So one of the main questions that actually keeps coming back is what is the ideal task distribution between humans and machines, and how to leverage both strengths and capabilities in the design process. It has been largely criticized that existing approaches to robotization usually aim at the complete substitution of human labor, where on the other side there is a growing understanding that not all processes can be automated, and there is rather a partnership model between humans and machines is beneficial, which is also true for AI systems. So questions such as how can we create real benefits by embedding human cognitive skills into the digital design process still are valid, and also like how to augment human decision-making process with machine intelligence. And also at which stage of the digital design to fabrication axis, which at the design end of this axis is related to the virtual aspects, so including topics of decision-making, information representation, and exchange, communication, and more, while the fabrication side of this axis concerns physical processes, so including but not limiting to material processing, localization, navigation, tolerances, robotic kinematics, and human-robot physical interactions. I guess Daniela's talk tomorrow will look more into the fabrication end of this axis, whereas I recently started to investigate more the design end of this axis. So let's first think about what's the difference in human-robot environments versus human-computer interaction in general. So in human-robot interaction, human and robot share the same workspace. The human operates in its native environment, so the physical world, And the slowness of physical material process deals well with human perception and understanding of the process. So additionally, the human can use its body-inscribed knowledge to perform tasks, which is supporting embodiment and situatedness, part of design. It is also essential to human-robot collaboration environments that they operate on the same artifact, so some kind of material system. Interaction systems for the user involved, hand-mediated systems, so gesture or touch. There is multimodal systems which involve multi-touch, speech, brain-computer interaction. There is some experimental systems which involve emotive, so measuring with EEG or haptic devices. And there is, of course, VR and AR-based systems. Now, if we exchange the robot with some general computer or some machine learning system, what are the differences? So obviously, robot and computer are technologically two totally different concepts, but for the purpose of simplicity, let's just make that experiment of thought. So they do not share the same workspace nor the same artifact, while human interaction modes may stay the same. Artifacts may be some high-dimensional data or design representation. And therefore, there is a transformation needed between the human and the machine learning system. And this may be immersive data design representation from the machine learning system to the user, and conversely, multimodal data annotation from the user to the ML system. So what I want to show you now are super current investigations into actually these two topics. I cannot present yet any results, so only early prototypes, but I want to present you the context where they are going to be used. So as Carla mentioned at the beginning, I'm actually part of this new Center for Augmented Computational Design in Architecture, Engineering, and Construction, short Design++, which is an initiative from 22 professors from different departments, so architecture, civil, environmental, biomatic engineering, and computer science. And in Design++, we focus on computational design methods to better integrate quantitative metrics such as structural integrity, energy performance, life cycle assessment, acoustics, and cost estimation with creative design. We use technologies of machine learning and extended reality to augment computational design process in architecture, engineering, and construction. Central to this lab, to this initiative is the lab, the Immersive Design Lab, which I'm co-leading. It's also a place to explore and create immersive synesthetic experiences. For example, you could create immersive spatial audio experiences using an audio system. You see actually 75 speakers mounted in this room. And we could use a 3D projector to project on a screen that has dimensions of 8 times 6 meters that actually reaches down to the floor, where you can watch actually 3D content through 3D active classes to like have that effect like in cinema. The lab's equipment also contains several head-mounted displays for AR and VR. So a big topic when working with machine learning systems is, of course, data representation. And a project where we studied this is data-driven acoustic design. In this project, we recorded the acoustic responses of 312 3D printed acoustic surfaces. We called our dataset the GIR dataset. So a geometry and real impulse response dataset containing 900,000 impulse responses, so approximately 3,000 per surface. This is the robotic setup we developed to measure those 3D printed panels. Per panel, we recorded approximately 3,000 impulse response at 72 defined measurement locations. You see in blue. And then different combinations of these 72 points resulted then into this full acoustic response. So actually per acoustic panel geometry, we have a rich and very high dimensional acoustic response. In order to understand this, we actually developed different post-processing methods to be able to compare the different panels with each other. As you see here, an indicator of reflected energy. Still, those demanded always a reduction in dimensionality and the transformation of the IR into a measure we called cumulative energy over time. This was kind of unsatisfactory because you need to flatten and reduce this high, rich data and information. So we explored different visualization modes to compare two panels with one another in order to understand the differences. So for example, here's an interactive 3D visualization bit with the time slider on the top. We also tested to visualize the data in VR, which allows you to get a better understanding. Of course, if you relate yourself to the data in one-to-one, and especially if you can interact and change different representation modi. So our goal next is actually to leverage the Immersive Design Lab and visualize and represent the data in VR and use the sound system of the IDL to discover this rich spatio-temporal information that is inside the data, supporting the understanding of acoustic diffusion, not only through the visual sense, but also through the auditory sense. And now, I simply want to note that such considerations are not novel. So for many of the groundbreaking technologies, we date back to the inventions in the 50s or 60s. So the fact that humans are multisensory in nature is something that Morten Heileck already in the 1950s explored for theater. So he developed the Sensorama, a mechanical device which includes a stereoscopic color display, fans, odor emitters, stereo sound system, and a motion mode chair. This was actually the first multisensory virtual reality apparatus. And here you see Norbert Wiener with a prototype of the hearing cloth for deaf people. The idea was that speech would be transformed into stimuli that deaf people would feel. So introducing yet another interesting area of data transformation between two different modal systems. The next topic is multimodal design and data annotation. So as acquisition, collection, and storing of data becomes cheaper and cheaper, human data processing, labeling, and annotation becomes a bottleneck for machine and deep learning because the performance and prediction of a model is significantly dependent on the quality of data and for training and validation of that model. And especially for design problems in the field of architecture, engineering, and construction, we usually have little data or incomplete data. So data annotation is important to embed this qualitative criteria into data sets and emphasize data that matters the most. Here also want to shortly explain the concept. So in our ongoing research project, AI, Augmented Architectural Design, we develop a toolkit for machine learning-based generative design pipelines. And we do this with a generic approach through several case studies that are based on two different design categories. One of these case study is actually, again, acoustic surfaces, but a special family of it, namely the ones we designed for the Immersive Design Lab, see in the back. They were developed to be 3D printed, so exhibiting one characteristic undulation in one direction, as you can see here in the picture. Back then, we measured it with the setup I've introduced before to decide on the best acoustic performative option. But now our acoustic research partners have developed an acoustic simulation. Together with the fabricability analysis, this boils down to 11 performance criteria that create a vast solution space where we can investigate different performance clusters. And now, one of the problems in generative design is, of course, the course of dimensionality. So there is just too many options. So now how do you embed qualitative criteria into the data set and emphasize data that matters the most? In this example, you see an interactive setup for design space browsing, where the data points are embedded into a UMap showing you clusters you can explore. On the right side, you see these parallel coordinates where both design parameters and performance attributes are stored. And you can also visualize the panels in 3D, which you can label then from 1 to 5 according to your liking. The idea is to use this data annotation further for active learning or for preferential learning. But actually, this is still happening in front of the screen, like one-to-one. Ideally, we can have a qualitative annotation to the data when we are fully immersed. I still thoroughly need to analyze the annotated data, but I realized that they're annotated very differently when going into VR, like analyzing and exhibiting this acoustic panel. Simply by the fact that I could experience the acoustic wall and its undulation in relation to my body. Like I said, it's an early prototype, but now the idea is that we do not only solely annotate such design variants with discrete numbers. We would like to annotate the design variant in the multimodal fashion. So human reaction to the presented design variant may be super obvious and conscious. So for example, the time spent on investigating, but can also be subtle and unconscious. So excitement measured through pupil size or heartbeat. So through such multimodal annotation, humans can attribute the design variant in a way more differentiated way. And maybe some notes on the system. So if you remember that communication system in the beginning for robots, sensors, and humans that is required for the information flow within the fabrication process, in here we also need to have a communication system. It may be only the infrastructure to the system, however, it also allows these flows of information to become explicit and comparable. And now I want to end my talk with highlighting yet another important aspect of data annotation. So humans need to be incentivized for data labeling in order to counteract fatigueness during design space annotation. And this is not necessarily related, but this is an art installation I made together with my colleague Katrin Dörfler for the Biennale in 2019. And here we intended to merge the spatial digital information with our existing physical environment. So we create actually digital garbage that one is cleaning up by moving the broom. This obviously does not necessarily make sense because digital garbage doesn't have to be cleaned up, but it's actually the point. So I had to start thinking about this merger of digital and physical spaces and how they can benefit from coexistence. Yeah, and then here you see some questions. Oh, yeah. Thank you.